Large language models, LLMs, are increasingly being used to reason over structured data tasks like classification, feature importance attribution, and even counterfactual reasoning. But here's a critical question. When an LLM performs well on a tabular benchmark like adult income or Titanic, is it truly reasoning, or is it simply recalling information it has seen before? This isn't just a technical detail. It's a fundamental threat to the validity of how we evaluate AI. In this video, we'll dive deep into a new study that reveals a hidden confound in LLM evaluations: semantic contamination, where models don't memorize data verbatim, but they do absorb the meaning behind it. And this has major implications for how we interpret intelligence in today's AI. Let's start with the basics. LLMs are trained on massive corpora: books, code, web pages, academic papers. Trillions of tokens scraped from the internet. The assumption has always been that these models learn general patterns, not specific facts. But what if some of those facts are not general? What if they're the exact datasets we use to test them? Take the adult income dataset. It's been around since 1994. It's featured in hundreds of tutorials, Kaggle competitions, and research papers. Same with Titanic. These aren't obscure datasets, they're cornerstones of machine learning education. And because they're widely published online, they're almost certainly present in the training data of modern LLMs. Now the big question: does the model know the data? To answer this, researchers designed a series of controlled experiments. They didn't just ask the model to predict income or survival. They tested how it performs under different conditions that isolate whether the model is relying on memory or genuine reasoning. The key insight: it's not about memorizing rows. It's about understanding meaning. They tested two tasks. First, the completion task. They masked 20% of the attributes in a record, say age, occupation, education, and asked the model to fill in the missing values from 5 options, 1 correct and 4 distractors. If the model gets this right, is it because it remembers the data, or because it understands that high income correlates with older age and technical jobs? Second, the existence task. They created fake records by randomly perturbing values, changing a person's occupation to something impossible or their fare to an unrealistic amount. Then they showed the model 5 versions of the same record, 4 fake, 1 real, and asked, which one is the original? The results were striking. On the completion task, models like Llama, Mistral, and QN, up to 32 billion parameters, achieved accuracies far above random chance, around 20%, on adult, Titanic, and credit card default datasets. Some models scored over 70% on adult income. But when they applied the same test to obfuscated versions, where column names were replaced with abstract labels like C01, C02, C03, performance dropped sharply to near random levels. Even more telling, in the existence task, all models failed. No model could reliably distinguish real records from fake ones. This means they don't memorize the data at the instance level. No verbatim recall. No exact matches. So what's happening? The answer lies in semantic contamination, not syntactic leakage. The model isn't remembering the rows. It's remembering the meaning behind the variables. It knows that occupation is a real-world category. It knows that fair is money. It knows that male and female are gender labels. It understands that high income is more common among men in tech jobs, even if it's never seen the exact data. This is why performance stays high on like datasets, synthetic data generated by sampling from marginal distributions. The model still gets it right, even though no actual records are present. Why? Because it's picking up on co-occurrence patterns, domain-level correlations, and linguistic semantics, not memorized facts. But here's the twist: when you strip away all meaning by replacing occupation with C01, education with C02, and so on, performance collapses. The model can't reason without the semantic scaffolding. This leads to a profound conclusion: LLMs don't remember data. They remember meaning. And that's dangerous for evaluation. If a model scores high on adult income, is it because it learned to reason about income prediction? Or because it's seen that dataset discussed in 10,000 blog posts, GitHub repos, and YouTube videos? The line between reasoning and recollection has blurred. And if we don't account for this, we risk inflating performance metrics, undermining reproducibility, and falsely claiming emergent intelligence. This isn't just about tabular data. The same issue affects code generation, vision language models, and even causal reasoning. But tabular benchmarks are especially vulnerable because they're so widely reused, unchanged, unhidden, and often presented with natural language column names. So what can we do? First, design contamination-aware benchmarks. Use synthetic datasets or obfuscated versions where semantics are stripped. Don't rely solely on canonical datasets. Second, include both semantic and non-semantic variants in evaluations. If a model performs well on the real dataset but fails on the obfuscated version, the high score likely reflects familiarity, not reasoning. Third, recognize that high accuracy doesn't equal generalization. A model that scores 70% on adult income might be doing so because it's seen the dataset in tutorials, not because it understands the underlying data structure. Finally, scale up the investigation. This study focused on models up to 32B parameters. Larger models, 70B, 100B, or beyond, may have even greater memorization capacity. We need to test whether contamination scales with size, and whether it affects more complex tasks like counterfactual reasoning or causal inference. In short, this research isn't about discrediting LLMs. It's about being honest about what they know and what they don't. The takeaway: when evaluating LLMs on structured data, don't just ask what they predict. Ask how they know it. Because in the age of massive pre-training, the most dangerous kind of knowledge isn't the data itself, but the meaning behind it. And if we don't account for that, we're not measuring intelligence. We're measuring exposure. So next time you see an LLM reasoning over a dataset, ask, did it learn it or did it remember it? Because in the end, the difference isn't just technical. It's philosophical. It's about what it means for a machine to understand data at all.